Collisions. When one body collides to another body, the event is called collision. First, elastic collision. In such type of collision, momentum of the system is conserved, while kinetic energy before and after collision is same. But the kinetic energy during collision time is not constant. Bodies move separately after collision. Second, completely inelastic collision. In such type of collision, momentum of the system is conserved while kinetic energy is not conserved, and colliding bodies move together after collision. 3. Inelastic collision. Momentum of the system is conserved while kinetic energy is not conserved, and colliding bodies move separately after collision. Collision in 1D. Elastic. Consider two bodies M1 and M2 is moving with velocity v1i and v2i. After some time it collides, and after collision its velocity becomes v1f and v2f. Then from conservation of momentum, m1 v1i plus m2 v2i equals to m1 v1f plus m2 v2f. This implies m1 into under bracket v1i minus v1f equals to m2 into under bracket v2f minus v2i. Equation 1. From conservation of kinetic energy, 1 by 2 m1 v1 I square plus 1 by 2 m2 v1 v2 I square equals to 1 by 2 m1 into v1 f square plus 1 by 2 m2 v2 f square. This implies m1 v1 I square plus m2 v1 I square equals to m1 v1 f square plus m2 into v2 f square. This implies m1 into under bracket v1 I square minus v1 f square equals to m2 into v2 f square minus v2 I square. This implies m1 into under bracket v1 I minus v1 f into v1 I plus v1 f equals to m2 into v2 f minus v2 I into v2 f plus v2 I. Equation 2. Dividing 2 by 1 we get v1i plus v1f equals to v2f plus v2i. This implies v1f equals to v2f plus v2i minus v1i. Equation 3. Using 3 in 2 we get m1 into under bracket v1i minus v2f minus v2i plus v1i into v1i plus v2f plus v2i minus v1i equals to m2 into under bracket v2f minus v2i. This implies m1 into 2 v1i minus v2f minus v2i into v2f plus v1i equals to m2 into v2f minus v2i into v2f plus v2i. This implies 2 m1 v1i minus m1 v2f minus m1 v2i equals to m2 v2f minus m2 v2i. This implies 2 m1 v1i minus m1 v2i plus m2 v2i equals to m2 v2f plus m1 v2f. This implies 2 m1 v1i plus v2i into under bracket m2 minus m1 equals to v2f into m2 plus m1. Hence v2f equals to 2 m1 v1i by m1 plus m2 minus m1 by m1 plus m2 into v2i. Similarly, we can calculate v1f equals to 2 m2 into v2i by m1 plus m2 plus m1 minus m2 by m1 plus m2 into v1i. Case 1. If body 2 is in rest, then v2i equals to 0. That is, body 2 is at rest. So from above equation we get v1f equals to m1 minus m2 by m1 plus m2 into v1y. That is velocity of first body after collision. This is the velocity of first body after collision, and V2F, the velocity of second body after collision, equals to 2m1 v1I by m1 plus m2. Sub case A, if two masses are equal, that is m1 and m2 are equal, then v1F will be equals to 0 into v1I equals to 0, and v2F 2m1 v1I by 2m1 equals to v1I. That is, after collision, first body come to rest and second body moves with initial velocity of first body. That is, after collision, body 1 comes to rest and second body moves with initial velocity of first body. Case B, if m2 is very very greater than m2, m1 is very very greater than m2, then m1 minus m2 equivalent to m1 and m1 plus m2 equivalent to m1. Hence v1F equals to m1 by m1 into v1I equals to v1I, and v2F equals to m1 v1I by m1 equals to v1I. That is, first body, that is velocity of initial body, first body after collision remains same, and the velocity of second body after collision becomes 2 times the velocity of first body. After collision, first body does not change its velocity and second body moves with double initial velocity of first body. Case C, if m2 is very very greater than m1, then m1 plus m2 equivalent to m2 and m1 minus m2 equivalent to minus m2. Hence v1F equals to m1 minus m2 by m1 plus m2 into v1I equivalent to minus m2 by m2 into v1I equals to minus of v1I. That is, first body reverses its velocity after collision, and v2F equals to 2m1 v1I by m1 plus m2 minus 2m1 v1I minus m2 equivalent to 0. That is, second body velocity after collision remains 0. Completely inelastic collision in 1D. Here m1 and v1I is the mass and velocity of first body, and m2 and v2I is the mass and initial velocity of body 2. After collision, both body sticks and move with velocity vf. So from conservation of momentum, m1 v1I plus m2 v2I equals to m1 plus m2 into vf. Hence vf equals to m1 v1I plus m2 v2I by m1 plus m2. Now initial kinetic energy of system Ki equal to 1 by 2 m1 v1I square plus 1 by 2 m2 v2I square, and final kinetic energy of system Kf equal to 1 by 2 m1 plus m2 to vf square equals to 1 by 2 m1 plus m2 into m1 v1I plus m2 v2I का होल स्क्वायर बाई m1 प्लस m2 का होल स्क्वायर इक्वल्स टू 1 बाई 2 m1 v1I plus m2 v2I का होल स्क्वायर बाई m1 plus m2. Hence change in kinetic energy delta K, Kf minus Ki. Putting the value of final kinetic energy and initial kinetic energy, we get finally minus delta K equals to minus m1 m2 by 2 into m1 plus m2 into under bracket v1I square plus v2I square minus 2 v1I into v2I, or equals to minus m1 into m2 by 2 m1 plus m2 under bracket v1I minus v2I का whole square. Negative sign indicates that final kinetic energy is less than initial kinetic energy. So after collision, energy is lost. The lost in energy is given by mode of delta K equals to m1 into m2 by 2 into under bracket m1 plus m2 into under bracket v1I minus v2I का whole square. Case 2, if second body is in rest initially, then v2I equal to 0. Thus lost is mode of delta K equals to m1 into m2 by 2 into m1 plus m2 into v1I square. collision in two dimension. If initial velocity of the body is not along the line joining the center of mass of the body, then after collision bodies move in different direction to the initial direction of velocity. Such type of collision is 2D collision. The situation is shown in the figure. From the conservation of momentum along x direction, we have m1 v1 I equals to m1 v1 f into cos theta 1 plus m2 v2 f into cos theta 2, equation 1. From conservation of momentum along y direction, 0 equals to m1 v1 f into sin theta 1 minus m2 v2 f into sin theta 2, equation 2. Now if the collision is lasting, then from conservation of kinetic energy, 1 by 2 m1 v1 I square equals to 1 by 2 m1 m2 v2 f square plus 1 by 2 m1 v1 f square, equation 3. We have three equations and four unknown theta 1, theta 2, v1 f, v2 f. So we cannot solve this problem. To solve the problem, we need one more known value. It can be done knowing theta 1 by moving the detector in xy plane. Now we can solve the problem.